Patch embeddings. So this is the second part of the video series where I'm making ViT from scratch. Now, patch embeddings is pretty simple. It's basically you break down an image into different patches and you, in a way, tokenize them. But that's not really the right technical word to use. But in the end, that's what happens. You kind of convert these images into tokens, which are something that a transformer can understand. A transformer does not expect images as inputs, right? A transformer expects tokens. Um, so that's what we'll be doing because transformer has a certain hidden dimension in its initialization where the input needs to be of the same hidden dimension so that the transformer can actually read it and process it and learn from it, etc. So before we jump into the code and all that, let's try to build an intuition for how this process happens. Let's say we have an image and in PyTorch we read images like this, that is batch size, channels, height, and width. And let's also look at a transformer model. A transformer model expects an input of this dimension, that is batch, features, and hidden dimension. So the hidden dimension and all these things can be set in the config file, which we'll be looking at later, much later in the series, right? All right. So the question is, how do we go from this dimension to this dimension in a meaningful way and not just tensor dot reshape, right? Let's break down what we have to do. We need to convert this image into multiple patches, and these patches will essentially combine to become one tensor, and we need to give that into the transform model, but with this dimension, which we have mentioned here, right? Let's do some fundamental operations to this input tensor. We want to convert it to patches, and these patches should not overlap with each other. For example, we can clearly see how this patch and this patch is unique, same as this patch and this patch. None of these tensors are overlapping each other, right? For this, what we can do is we can apply a convolution. Let's see what we can do here. We can apply a conv2d where the number of incoming channels. All right, before we do that, let's assign some numbers so that we don't work with variables. Let's say we have batch, we have channels as 3 and height as 224 and width as 224 as well, right? And let's look at the transformer. We can assign some numbers here as well. That will be batch size. Let's say features are 196. This will make sense towards the end. And of course, this can change and be whatever it is. But this is 768. So how do we go from this to this is the question. To create patches, we can apply convolution and to make sure, and let's say we want 16 cross, we want 16 patches, right? From this image. So what we can do here is the incoming channels will be 3 because obviously that's the number here. The outgoing channel, I mean the output of the convolution will have this many number of channels. That is the hidden dimension. So that will be 768, right? Since the original paper converts the patches to 16 cross 16, as in the title of the paper is an image is worth 16 cross 16 words. So we're going to use that as well. So for kernel size, we'll be using 16, and for strides, we'll use 16 as well. So the idea of using kernel size and stride both is that we can avoid the overlapping patches. We can only take patches which are unique and which are adjacent to each other. So we take this, then we have a stride of 16 cross. So I'll change the color. Let's say, okay. So we take this, then we move 16 cross 16, then we take this, move 16 cross 16, we take this, move 16 cross 16, and this goes on. Essentially, we convert the entire image into these 16 cross 16 patches, right? If we want to convert 224 into this, we can come to the conclusion that 224 by 16, we know that this is 14. So the post convolution, this tensor will look something like this. This tensor, which we gave as input, will look something like, right. Now we want to take this tensor and we want to get this tensor out of it. We know that 196 is 14 cross 14 into 14, right? So what we can do is we can apply a flattening here across the second dimension because this is 0, 1, 2, 3. So when we do that, we end up with batch size 768 and 14 into 14, which becomes batch size 768, 196. All right, we're getting somewhere. All we need to do now is a transpose of 1 and 2, where this is 1, this is 2, this is 0, 1, 2, right? So if we just switch this with each other, we finally end up with the dimension we need, that is batch size 196 and 768. This is the same dimension as this, and now this is something that the transformer can understand, the transformer can learn from. Essentially, we have converted an image into tokens which can be processed by the transformer, right? Of course, we'll be adding positional embeddings to this, but we'll look at that in the next part. This is just an introduction to how we do the patch embeddings. If you look at the code for this, it's pretty straightforward. We have a class called Patch Embeddings. We declare a bunch of default values. And for simplicity, I've used the same default values which I've used in the example uh, in the previous screen. Inputs is 224 cross 224, patch size is 16, and number of input channels is 3. Output embedding dimensions are 768. Now, we declare a convolution where the number of incoming channels are number of channels, that is 3. The number of output channels are embedding dimensions, that is 768, and thus the kernel size and the stride are both 1616 and 1616. This is, as I explained before, to avoid overlapping patches. Now, when we go to the forward or the implementation of this class, we get an input image. We do input image.shape to read the inputs, batch size, num channels, height, width. We can use this height width to create an assertion statement to make sure that the user inputs only the images which are resized and correct images and not unresized random images. We return self.projection of input image dot flatten of 2 dot transpose of 1 comma 2. As explained in the previous slide, self.projection is the convolution. So we apply the convolution first to the input image. Then we do a dot flatten of 2, which converts. So the input we get is batch size, channel, height, and width. After the convolution, we get batch size, embedding dimension, height, and width. This is a different height and width. It's not the same. I should probably not use the same alphabet, but yeah. This is then converted into batch size embedding height into width using the flatten of 2. Then we do a dot transpose of 1 comma 2, which converts this to batch comma height into width comma embedding dimension, and that is basically your input to your transformer. So this is basically the code and the theory behind what patch embeddings are and what this layer does. Hope this is clear, and in the next section we'll be looking at how we do how we create positional encodings and add this to these patches and then give it to the ViT or the transformer for it to learn.